Hello again, and welcome to our continuing study of logarithmic and exponential functions. We've developed both the natural logarithmic function and its inverse, the function e to the x. And we observe one of the amazing properties of e to the x, that it's equal to its derivative. So today we're going to look at exponential and logarithmic functions to different bases. These are probably some of the functions you saw in your pre-calculus courses. For example, the logarithm to the base 10. These functions are more complicated in calculus. The formulas for derivatives and integrals are not nearly as pleasant as the ones for e to the x and log x. Fortunately, the properties of these functions will be similar to our pre-calculus properties. But again, you'll find some of the formulas unpleasant, and I'll talk about that issue as we go along. And then also we'll intersperse this lecture with some applications, one to half-life of a radioactive material and the other to compound interest. So let's remember where we are here. We defined the function log of x and its inverse e to the x. These are inverses of each other. Their graphs are symmetrical, are mirror images of each other about the line y equals x. Now we're going to define the exponential function to a different base, not e to the x, but say 2 to the x. And here's the trick. Here's how you do it. You define 2 to the x in terms of e, and that will permit us to find derivatives of 2 to the x. So here's the definition of 2 to the x. Remember that we could rewrite it as e to the log of 2 to the x, because log and e are inverses. So if I do e to a log, those cancel each other. So why would I make things more complicated? Well, now I have log of 2 to the x in the exponent, and the x can slide into the front by the properties of logarithms. So 2 to the x can be defined in terms of the exponential function as e to the x log 2. It's e to a power. Isn't that interesting? Here's the general definition of a to the x, where a is a positive real number, and usually you assume that a is not 1. The definition is a to the x equals e to the power log a times x. This function, a to the x, obeys the usual properties of exponents that you learned in pre-calculus. Notice that this definition simplifies a lot if a happens to be e. Remember, e is kind of our magic number. If you replace a with e in that equation, look what you get. The left-hand side would be e to the x, and the right-hand side would be e to the log e. Log of e is 1. Log of e is 1, and so it's e to the x. So this is a generalization of e to the x. Let's pause and do an application where we see that using a base different than e can be useful. Well, it turns out that the half-life of carbon-14 is about 5,715 years. So suppose you have a sample of carbon-14 that contains, well, a sample of material that contains 1 gram of carbon-14. How much carbon-14 will be present after, say, 10,000 years? Well, here's how half-lives work. After 5,715 years, you'll only have half a gram. In other words, half of it decays away. You start with 1. After 5,715, you'll have half a gram. And then in another 5,715 years, you'll have a fourth of a gram. That means that in 11,430 years, that's 2 times the half-life, in that many years, you'll have a quarter of a gram. So what should we expect after 10,000 years? Well, we should expect to have a little more than 1/4 of a gram, shouldn't we? So let's model this situation and see what the answer really is. Here's an interesting model of the half-life of carbon-14. Y equals 1/2 to the power T over 5715. So Y is the amount of carbon-14 at time T. Let's check this model to see if it works. How much is there in the beginning when T is 0? Well, 1/2 to the 0 power is, of course, 1. Anything to the 0 power is 1. How much is there after 5,715 years? Well, replace T with that number, and your exponent is now 1. And so Y is equal to 1/2. Great. You can see how it works. Every time you have every interval of 5,715 years, you go down by a factor of 2. So all you have to do now is plug in 10,000 for T, and on a calculator, calculate 1/2 to the power 10,000 divided by 5,715, and you get approximately 0.3 grams. That's how much carbon-14 is left in your sample after 10,000 years. Good. We've done the exponential function to a different base. What about logarithms to a different base? Well, we're going to assume that our base is a positive real number, and again, we won't use a base of 1. And here's the definition of logarithm to base A of x. It's defined to be 1 over log A, natural log of A, times the natural log of x. In other words, you define the logarithm to base A in terms of the natural log to base E. You might recognize that formula from your pre-calculus days. That's the change of base formula that you might have used in a course on logarithms when you're changing from one base to another. In a sense, we're changing from base A to base E. So there's our official definition of logarithm to base A. If you look at your graphing utility, your calculator, you'll see a button on there for logarithm to base 10, and you'll see another button for the natural logarithmic function, because both of these functions play a big role in applied mathematics. In calculus, log base E is much more important than log base 10, but both buttons are on graphing calculators. Fortunately, the logarithm to base A satisfies all the properties of logarithms that you learned to love when you were taking algebra. For example, the logarithm of a product is the sum of the logarithms. The logarithm of 1 is equal to 0. The logarithm of A to base A, the logarithm base A of A is 1. The logarithm of x to the n has that same formula as before. You can move the n out to the front, and it's n logarithm of x. And the logarithm of a quotient is the difference of the logarithms. Good. It turns out, you would expect this, that the logarithm to base A and the exponential function a to the x are inverses of each other. They are reflections across the line y equals x, just like e to the x and the natural logarithm functions are inverses of each other. You can verify that as follows: logarithm base A of a to the x. So I'm composing a to the x with logarithm, slide the x out to the front, and then log base A, of course, is 1, so I end up with just x. And in the same way, a to the power log base A of x equals x. Good. So those are the inverse relations. Here's a graph of 2 to the x, which sort of looks like e to the x, and the graph of log base 2 of x, which sort of looks like our natural logarithmic function. And they are reflections of each other along the line y equals x. Good. I can't emphasize enough the common mistake that I see where students will write that the logarithm of a sum is the sum of the logarithms. That's not true with the natural logarithm, nor is it true with any logarithms. The log base a of x plus y is not the sum of the two logarithms. In fact, you really can't simplify the logarithm of a sum. You can simplify the sum of logarithms. In fact, it's the log of their product. Okay, so be careful with that. That's something to always try to remember when you're taking a calculus course and dealing with logarithms. It's a very common mistake. Let's do some equations now involving our logarithms and exponential functions to different bases, just to practice some of the manipulation skills. Suppose you had an equation 3 to the x power equals 1 over 81. What's x? Can you find x? Well, it's up there in the exponent. How can I bring it down to earth? Well, here's one way. Take logarithms to both sides, but make the logarithm to the base 3. The advantage of that is the left-hand side becomes log base 3 of 3 to the x, and those are inverses of each other, and so the left-hand side is just x. And the right-hand side is log base 3 of 3 to the minus 4. I got that by saying log base 3 of 1 over 81, and 1 over 81 is 3 to the minus 4th power. And now I have log base 3 of 3 to the minus 4. The inverse property again says that that equals minus 4. That's your answer. Good. Let's do another example. How about solving for x if log base 2 of x equals minus 4? So now the x is kind of hiding in the logarithm. How can we get it out of the logarithm? Well, one way would be raise both sides to the power 2. In other words, 2 to the log base 2 of x equals 2 to the minus 4 power. Why did I choose 2 here? Well, I'm doing a log of base 2, so I'm going to do the exponential function that's the inverse of that, which is 2 to a power. So the left-hand side has a cancellation and leaves just x. And the right-hand side is 2 to the minus 4th, which is 1 over 2 to the 4th, which is 1 over 16. Good. So I hope we're comfortable with solving some of these equations. And by the way, there are other methods for solving logarithmic and exponential equations, and they all will give good answers. Great. Let's turn to calculus now. We have these new functions, a to the x and logarithm base a. What are their derivatives? Well, the derivative of a to the x is easy to find because we can replace a to the x with its definition, which involves the exponential function e to a power. So a to the x equals e to the log a times x. So now I have to differentiate e to the log a times x. Well, that's a simple chain rule. The chain rule says it's e to the same power, e to the log a times x, times the derivative of the exponent, which is log a. And now that first part of my answer, e to the log a times x, is nothing more than a to the x. And so the final answer is log a times a to the x. You can see why the base a is unpleasant. That's not a very pretty formula. It's much nicer if it's e to the x. And you can see why. If it's e to the x, then in the formula, the log a becomes log e, which is 1. So it is unpleasant when you're dealing with different bases. It's going to be unpleasant also with the logarithm function. The derivative of log base a of x is the derivative of its definition, which is 1 over natural log of a times log x. So the final answer is 1 over log a times the derivative of log x, which is 1 over x. So those are two formulas that are a little more complicated than I would like as a mathematician. I hope you see why in both these cases, E is the preferred base. It simplifies the formulas. Let me summarize them in a different notation. A to the x prime, in other words, the derivative of a to the x is log of a times a to the x. Log base a of x prime, in other words, the derivative of log base a of x equals 1 over log of a times x. Unpleasant, complicated formulas. Should you memorize these? Well, I sort of don't think so. A lot of my students have very good memories, and they know all these formulas when they come to calculus class. They just memorize them, and they can use them freely. I don't have such a good memory. I kind of rely on being able to derive the formulas when I need them. I remember the definition of a to the x, and hence I can derive this formula if I ever have to use it. A personal note here, I'll admit something to you. I used to be a chemistry major when I was in college, my first 2 years at Stanford. And then I took organic chemistry my sophomore year, and it had so much memory that I just couldn't handle it. A lot of those benzene rings and things, it just really boggled my mind. And I said, uh-oh, I'm not going to be successful in chemistry. What can I do? And I had taken a lot of calculus simultaneously with my chemistry classes because the chemistry major required calculus. We were using calculus in the chemistry classes. And then I had all this calculus, and I talked to an advisor, and the advisor said, hey, why don't you be a math major? And here I am. Good. Okay. Enough personal asides. Let's do some more examples to make sure we're comfortable with these fairly unpleasant formulas. What's the derivative of 2 to the x? Well, it's log 2 times 2 to the x. You have to put that extra logarithm in there. What's the derivative of 2 to the 3x? Now it's even a little more complicated. It would be log 2 times 2 to the 3x times the derivative of the exponent, which is 3. So an extra 3 comes out, and the final answer is 3 log 2 times 2 to the 3x power. How about a problem involving logarithms? What's the derivative of logarithm to the base 10 of x? Well, it's 1 over the log of 10, that's the natural logarithm of 10, times x. So the denominator is 1 over log 10 times x. A fairly unpleasant answer because the base is not e. How about, here's a worse one. What's the derivative of log base 10 of the cosine function? It would be 1 over log base 10 of cosine, 1 over the thing, and you put the log base 10 in there, and then you have to differentiate cosine by the chain rule, and you get minus sine x. So the final answer is minus 1 over log 10 times the tangent. Sine over cosine is tangent. Well, there's even more. Sorry about all this, but there's even a formula now for the integral of a to the x. How would you get the integral of a to the x, or the antiderivative of a to the x? Well, if you know the derivative, then you know how to get an integral formula. So the integral would be 1 over log a times a to the x plus a constant. Why is that true? Think about it. Differentiate the answer. The derivative of a to the x is log a to the x. And the log a's cancel, don't they? So this must be the right formula. Again, it's not a formula I would suggest you memorize, but you can sort of figure it out. If you know the derivative formula, you'll know the integral formula as well. And finally, let me repeat, I hope you see why E is the preferred base in calculus. All these formulas simplify if A is equal to E. You might be asking also, is there a formula for integral of log of x, log base a of x, or even the natural log of x? We don't know yet. We have to tune in later. In a later lecture, we'll talk about that question. Let's do a couple of examples to apply these principles. Here's a very simple one. What's the area under the curve y equals 2 to the x between 0 and 2? Okay, how would you do that? You imagine 2 to the x, it's an exponential function going upwards, and we're finding the area between 0 and 2. That means we have to integrate 2 to the x between 0 and 2. So what's the antiderivative? Well, it was that formula I just talked about. It's 1 over log 2 times 2 to the x, and the limits of integration are 0 to 2. So I plug those limits in. I get 1 over log 2 times the quantity, 2 squared, that's plugging in the top limit, minus 2 to the 0 power. And 2 squared is 4, minus 1 is 3, so it's 3 over log 2. That's the area under that curve. Good. I'm now going to move to a seemingly different topic. We're going to talk about a limit that's really fascinating. It's the function 1 plus 1 over x to the x power. And you might say, whoa, where's this coming from? Stay with me for a few minutes and you'll see something really fascinating about this function. 1 plus 1 over x to the x power. And I ask the following question. What's the limit as x goes to infinity? In other words, what's its horizontal asymptote? Now, some of you might argue as follows. This is 1 plus something really small, because x is going to infinity. And 1 plus something small to the infinity power, well, it's a little bit bigger than 1 to a big power. Maybe the answer is that it goes to infinity. But others might say, well, it's 1 plus something negligible to a large power. 1 to any power is 1. So you might think the answer is 1 to this problem. Well, if you use a graphing utility and plug in large values of x, you discover that the limit is in between 1 and infinity. The limit's e, our old friend e. Wow. In fact, many textbooks use this as the definition of the number e. It's an amazing result. This number e appears all over mathematics. And here's a definition of it. It's the limit of that function as x goes to infinity. Good. Let's apply that to finance, compound interest. And then I'll give you some advice if you're ever a banker. Let me remind you about how compound interest works. Suppose you have P dollars and you deposit it in a bank that pays compound interest, and they compound it n times per year. Then the formula for how much money you have after 1 year is the following. It's P times the quantity, 1 plus R over n to the n. R is the interest rate, and you express it in decimal form. A is the amount after 1 year. And n is the number of times you compound per year. Let me show you an example of how this works, a very specific, with numbers. Suppose you have $1,000, and it's 8% interest, which it's a pretty good interest rate, which we write as a decimal, 0.08, and suppose it's compounded every 6 months, so it's compounded twice a year. How does it work? After the first 6 months, here's how much money you have in your account. You have the original $1,000, plus you've earned some interest. Now, you didn't earn 8%, you earned half of that, 4% for the first 6 months. So you've earned 1,000 times 0.08 divided by 2. And so that, if you factor out the 1,000, after 6 months, you have 1,000 times the quantity, 1 plus 0.08 over 2, which is exactly $1,040. So you've earned some interest. Now, here's why compound interest is so powerful. How much money do you have after 6 more months? At the end of the year, in other words. Well, here's how much money you have. You have the amount you earned after 6 months, which was 1,000 times 1 plus 0.08 divided by 2. And then you earn interest on that amount. Well, how much interest do you earn? It's that amount times the interest rate. So it's 1,000 times 1 plus 0.08 over 2 times the interest rate, which is not 8, but rather 4, 0.08 divided by 2. And now factor again. Factor out the 1,000 times 1 plus 0.08 over 2, and you're left with 1 plus 0.08 over 2, and then you can compactify that into 1,000 times 1 plus 0.08 over 2 quantity squared. And that was the original formula. And that turns out to be 1,081.61. Notice it's a little more than 8% because we compounded. It wasn't just $80 of interest, but you made 81.61. So that was compounding twice a year. Suppose I compound 10 times a year, 20 times a year, 50 times a year. I'm going to compound more and more frequently. Let's see what happens to my formula. Remember, the formula is P, the amount you deposit, times the quantity 1 plus R over N to the nth power. And I want to know what happens when N gets large. Take the limit as N goes to infinity. And I'm going to now manipulate that equation a bit. It's 1 plus R over N, which if I put that in the denominator becomes 1 over N over R. You see how that fraction got flipped? Now I do the following. I take that equation, 1 plus 1 over N over R, and the power used to be N, but I want the power to be N over R, so I put N over R there and then put outside an R so I don't change the problem. So I multiply and divide by R, in other words. Now, this is N going to infinity. Imagine in your mind that X equals N over R. So as N goes to infinity, N over R goes to infinity, so X goes to infinity. So I can rewrite this as follows. It's P times the limit as X goes to infinity of 1 plus 1 over X to the X power. And then there's an R sitting way outside. Do you recognize that character sitting there? That's our friend E. That limit is E, 1 plus 1 over X to the X. Wow. So this collapses to P E to the R. And that's called continuous compound interest. It's compounding continuously. Not 1,000 times a year, not 1,000,000 times a year, but continuously. So let's do a quick problem on this. Suppose you have, well, let me show you the formulas then for compound interest and continuous compound interest. For compound interest, for t years, it's the same formula as before, but you add a t in the exponent. So it's p times the quantity 1 plus r over n to the nt power. And for compound interest continuously, it's pe to the rt. You add the t in the exponent as well. So here's an example. Suppose you have $2,500 at 5% interest for 5 years. Okay? $2,500, 5% interest for 5 years. Suppose you're compounding 4 times a year. How much money do you have? The formula says it would be 2,500 times the quantity, 1 plus 0.05, that's the interest rate, divided by 4, because it's 4 compoundings, to the power 4 times t, 4 times 5. So the exponent is 20. And if you do a calculator, that's $3,205.09. How about 12 compoundings? Well, that turns out to be $3,208.40. A little bit more, $3 and something more. How about continuous compounding? Well, now it turns out to be $3,210.06. A little bit more, isn't it? So if I were a banker, I would tell my customers, come to my bank and deposit your money because I don't compound it once a year or twice a year or 4 times a year or monthly. I compound it every second or every millionth of a second basically saying continuous. And the amount of money and interest I would have to pay out to these customers is not much more than if I were compounding 12 times a year. So you see that continuous compounding is, you get more money that way, but not a whole lot more. Good. We did a lot in this lecture, and it was difficult material because we had these unnatural bases that were not the number e. The calculus of these functions was difficult, but we saw some applications where the exponential and logarithmic functions were quite important. Next time we're going to look at inverse functions again, and we're going to look at the inverse trig functions. Earlier, in an earlier lecture, we observed that the sine function was not one-to-one, so we'll have to restrict some domains to construct these inverse trig functions. I think you'll enjoy next lecture, so I'll see you then. Thank you very much.